Yes. All right. So we're going to start off with pericyclics. So these were the newest, or like the first thing that you guys covered after exam 3. And so as you may remember, there are 3 types of pericyclic reactions. So we'll go through each of them one by one. So first, you're going to have your electrocyclic reactions. So there are a couple definitions that you want to keep in mind for these reactions. So first, as you should remember from Orgo 1, HOMO is your highest occupied molecular orbital. Your LUMO is your lowest unoccupied. And then something new that you guys covered this year was what a photochemical HOMO is. So this is just what your old LUMO would have been. And this would be under light conditions. So basically, if you apply light, it'll excite one of your electrons into a higher orbital state. And so that's why your old LUMO becomes the photochemical HOMO. And then another concept just to keep in mind are frontier orbitals. And these are the atomic orbitals involved in sigma bond formation. Okay, so we'll start off with a little bit of an example of how to draw your pi MOs. So your MO diagrams will be based off of a pi system. So if we take, for example, this 4-atom pi system, that means that we're going to have 4 levels of pi orbitals. So we can go ahead and draw those out. Okay. And then based off of the rules of symmetry, you can go ahead and fill in the orbitals. So in my pi 1, all of them will be filled on the same side. In my pi 2, I'll have 1 node, so I'll flip it once. In my pi 3, I have 2 nodes, and it becomes symmetric again. And then in my pi 4, I'll have 3 nodes. So from here, now I'm going to figure out which one is my HOMO and which one is my LUMO. So if we're operating under heat, that would be what we consider our normal conditions. So if we have 4 atoms and 2 double bonds, since there are a total of 2 electrons in each double bond, we have 4 electrons to fill. And so I'll go ahead and start from the bottom and fill those. So now we know that our pi 2 would be our HOMO, and then our pi 3 is our LUMO. Next, if we are under UV light, we're going to be using a photochemical HOMO. So this occurs when one of the electrons from our HOMO gets excited up towards the next level. And so this level becomes our photochemical HOMO. And it aligns with the pi system that used to be the LUMO. All right, so now if we try some examples, if we're using this 4-atom pi system, we can go ahead and draw out where the HOMO is. And so let's assume that we're operating under heat right now. So we're just going to be using our pi2 level. And so now you get to do your finger gun things. So for these to work, we're going to pretend that our thumbs are the orbital directions, and then our pointer fingers will be those R groups. So looking on this left-hand side, the thumb is pointing upwards, and then your pointer finger is pointing outwards. And then on the right-hand side, your thumb is pointing down to match the orbital, and then your finger is pointing outwards to match the R group. And so in order for you to form a bond between these orbitals so that they overlap, you're going to rotate inwards. And then you'll notice that your fingers are pointing in opposite directions. So that's what you need to know for your stereochemistry. So when these two bonds rotate inwards, then your fingers will be going in opposite directions. So that way, when you create your final product, they should be a wedge and a dash so that they're opposite each other. Okay. And then another term that might come up is that this rotation is called con rotation. Sorry, guys. And that's just because you're rotating in the same direction. Cool. All right, now let's try it under UV light just to see how it changes. So let's say that we have the same starting material, but we're now applying UV light. That means that up here, we're going to be using our photochemical HOMO. So we'll be applying a pi3 MO diagram. Okay, so then following the symmetry of that, we'll fill in our orbitals like this. And then you do the same finger gun thing. So on the left-hand side, your orbital is pointing upwards and your finger's going out. And then on the right, it's the same way. So then when you rotate your orbitals together, they're both on the same side. So then given that they're both on the same side, you know that they should either be both wedged or both dashed. It doesn't matter which. And then the term for this one, since you're rotating in opposite directions, is disrotation. Okay, cool. So that was just a brief overview of electrocyclic reactions. I'm going to keep moving if there's no questions on that. Okay, so the next type of pericyclic reaction that you guys went over is cycloaddition. So there are two types of cycloaddition that you guys want to consider. You're going to have your 2+2 reaction. And so if we take, for example, two double bonds and add them together, let's first try adding them under heat. So we have to do a pretty similar thing as what we were doing for the electrocyclic reactions. And this time we want to draw out the HOMO and the LUMO of each of the molecules. It doesn't matter which one's your HOMO and which one's your LUMO because it'll still work. So under heat, we'll be using the normal HOMO, which is just filled on top. And then your LUMO will be opposite. Okay. So what you'll notice here is that you will not have overlap because your orbitals do not match each other. So these two are both up, which works, but then this other one is up down, so they won't overlap properly. And so if you're doing a 2+2 reaction under Okay. If you're doing a 2+2 reaction under heat, you will not have a reaction. Instead, let's try it under UV light. So under UV light, you're going to be using your photochemical HOMO and then your LUMO. And so since your photochemical HOMO is just like your LUMO, you're going to be using this pi system, pi orbital, sorry. Okay. And then what you can see here is that you can overlap them, or like the orbitals will overlap. So you have both up on this side or both down on this side. And so you can form a bond in between them. And then that's when you would get your reaction to form a box. Then the next type of cycloaddition that you guys should remember is a 4+2. And this one will look very familiar to all of you guys by now because it's just your classic Diels-Alder. So we'll do the same process for this one. If we have a 4+2 operating under heat, let's take a look at the MO diagram for this. So we'll use the HOMO up here and then a LUMO down here. Again, it doesn't matter which one you choose. Okay. So in this configuration, you'll see that you'll have overlap between the two upwards one and also the two downward orbitals. And so this is when you'll have your Diels-Alder reaction to create your 6-membered ring. Okay. If you try it instead under UV light, we can see how the orbitals line up. And so in this case, we'll use our photochemical HOMO and the LUMO. And so this one will instead look like this. And then here you can see that there will not be any overlap, which means that there's no reaction. Cool. Okay, so those are your two cycloaddition reactions. And then lastly, the third pericyclic reaction is your sigmatropic rearrangement. And for these, there are also two that you should know. One of them is a 1,5 rearrangement. And so if we have an example molecule, like that, the most important part of the sigmatropic reactions is just numbering your atoms. And so your hydrogen and the carbon adjacent to it will be numbered 1, and then the rest will be numbered in order. And so then once you do your arrow pushing mechanism, those bonds will shift over and then you'll form a new 1,5 bond. And so then your product will just be the same molecule, but flipped. Okay. Cool. So just key thing to remember is that your sigma bond forms between your 1,5. All right. And then your second type of sigmatropic reaction, that is the wrong color, is your 3,3 reaction. So if we take another molecule your oxygen and then the carbon adjacent to it will both be labeled 1, and then the rest are labeled in order. So once you push your electrons around, you'll be forming a new bond between your 3-3 position. Okay. Cool. So those are all of your pericyclic reactions that you'll need to review for the exam. Are there any questions on this segment? Okay. Does anyone need me to scroll back up to anything either? Because we're going to be switching gears now.
Can you go back up to Diels-Alder, please?
Yes.
Okay, thank you.
Okay. We'll have time for more questions at the end too if it wasn't covered yet, but let's switch over to the biochem area just because there's also a bunch of content to cover there. So we're going to be going into a lovely PowerPoint instead. So yes, biochem, proteins. I don't know what these are. They're proteins. All right, so we'll start off by going over a review of amino acids, and then we'll go into carbohydrates and then a bunch of reactions that you guys need to know. Yeah, so we'll go ahead and start off with some review of stereochem. Wait, it's not me, but okay. So starting with amino acids, just remember that you do need to understand the stereochemistry of the ipsocarbon. So what is the ipsocarbon? It is the carbon that attaches to the nitrogen and then also your carboxylic acid. So this guy right here is going to be the chiral center. And then using all of your Orgo 1 knowledge that you should remember, you will be able to figure out the stereochem, the absolute configuration of that carbon right there. And then just by convention, if you have an S configuration, you will be calling it an L amino acid. And if it is R, it'll be called a D amino acid. Cool. And then also just remember that we have Fisher projections. So these are a very common way of showing molecules in bio. We're going to see them a lot with amino acids as well as carbohydrates later on in this PowerPoint. And then remember that when you're representing Fisher projections, they show you where the molecules are oriented in 3D space. And so if they're on the horizontals, they'll be coming out towards you. And then if they're on the verticals, they'll be going back away from you. Okay. And then once we get to the carbohydrate section, we'll be converting between Fisher projections to Haworth projections so that you can create cyclic molecules as well. Okay, cool. Brief review on stereo. If you don't remember that stuff, I would recommend that you review it from your Orgo 1 notes. Next, we'll go into the isoelectric point. So for Falzone's class, you do not need to memorize individual amino acids, but you should be able to characterize the side chains. You do not need to memorize pKa's as well. They'll be given to you on the exam if you need them. So those will be good hints as to whether or not the side chains are neutral, acidic, or basic. Okay. And then your key concept for this section is what the isoelectric point is. And so that is the pH at which the molecule has a net neutral charge. And so if you were to count up all of the charges on the molecule, it should equal 0, or it will equal 0. So then next we want to consider how do we figure out what the PI of an amino acid is. And so this process is just taking the average of different pKa's, but it differs based off of the amino acid type that you have. So if you're using an amino acid with a neutral side chain, that means that you'll only have two pKa values. You're going to have the pKa value of the amine and then also the carboxylic acid. So then the way to figure out your PI is just to take the average of those two values. Okay. All right, so then next we want to consider how to create one of those titration curves that you guys probably saw in one of the problem sets. And so we'll start by looking at this. When you have a titration curve, I think it's easiest to start from the bottom and move up by each half equivalent of base. So at your first half equivalent, that is the pK, you'll be at the pKa of turning the acidic group from your protonated version to your deprotonated version. So in this example with leucine, you'll be converting your carboxylic acid, so that's the acidic group that you have, into your deprotonated version. Okay. At the next half equivalent of base, so we're at this 1 position, that is what your PI will be. So the value that you just calculated is your PI, and that is where you're going to have a net neutral molecule. Okay. And then at your next equivalent, you'll be switching your basic group. And so your basic group will go from its protonated version to its deprotonated version. So that's what's happening with this nitrogen right here. Okay.
Will it always be the one equivalent of base as the PI?
So it depends on if you're using what type of side chain you're using. So I'm going to keep going forward to the two other types of side chains, and then you'll be able to see how it differs a little. Okay. This next slide has a more in-depth progression up through the titration of leucine. So underneath this first part, if it'll click, okay, you have the fully protonated version. And then, like I said right before this, once you hit that first half equivalent of base, you're going to deprotonate your carboxylic acid into its deprotonated version, but your acidic group, And then at your PI, you'll have a net neutral molecule. So you see that your plus and minus charge will cancel out. In the next area, you're going to be deprotonating the basic, the amine group, but you're going to have a little mix of both. And then once you get above it, you're going to have fully deprotonated it completely. Okay. So then those were for neutral side chains. The same process pretty much happens for acidic side chains. But in this case, you're going to have 3 pKa's listed for your amino acid. So to calculate your PI, you'll just be taking the average of the 2 lowest pKa's. So for example, when we look at this amino acid, we're going to be averaging your 2 lowest. So it'll be this carboxylic acid on the right and then the carboxylic acid on the left. Okay. And then the titration curve right here, you'll do the same process. You'll plug in your pKa, your lowest pKa first at your half equivalent. At your 1 equivalent of base, you'll hit your PI, and then so on up. Okay. And then for basic side chains, you'll do the same process. But in this case, you'll have 3 pKa's again, and instead of averaging the 2 lowest pKa's as you would for your acidic amino acid, you'll instead average the 2 highest pKa's. So for example, when we look at this, we'll be taking the 2 highest pKa's, so it'll be of this amine and then this amine to get our PI. And then here is where it's a little bit different. Your PI will hit at the second full equivalent of your base. So you'll have your pKa of your carboxylic acid at your 0.5 equivalent. And then at 1.5, this is your pKa of your other amine group. Your pi will be at your second full equivalent of base. And then at the next half equivalent will be your pKa of the second side chain. Okay. So now we have a quick summary slide. Your isoelectric point is where you have your net neutral molecule. Your pKa is where you get the pH that you get deprotonated as you add a base. And then in order to calculate your isoelectric points for different side chains, when you have a neutral side chain, you should take the average of the two pKas. For acidic ones, you'll take the two most acidic, so your two lowest pKas, and then for basic, you'll take the two highest. And then for your titration curves, you're going to be moving every half equivalent of base. Okay. Any questions on PI or any of those calculations? Okay, chill.
I have a question. Will your side chains like generally be within like your primary like OH and NH or NH3, like the pKs of your primary amino acid?
Wait, sorry, I don't think I fully understood your question.
Like, will the pK of that side chain like be between the two pKas that are like of your like the general form of your amino acid?
I don't want to say always, but I don't have them memorized. I wouldn't be too concerned about it because you'll be given all of the pKa values on the exam. So they'll be denoted and you'll like just see where they are.
Okay, thank you.
Yeah. Okay, cool. Feel free to put any questions in the chat and the other leaders will grab them too, because I'll be moving on to carbohydrates. So this is like a lot of what you guys have just learned. So we're going to start off with projections and conversions, just so that we can be able to move between different the same compound in different viewpoints while maintaining the same stereochem. So our three most common are going to be your Fisher projection, your Haworth projection, and the chair conformation. And so we want to be able to convert between these and make sure that all of the stereochemistry remains the same because they are the same molecule. So firstly, just want to cover numbering of carbons, because this numbering convention is standard and you should be using it. Otherwise, IDK, it'd probably be pretty hard. So just remember that when you're starting from your Fisher projection, the top carbon will be 1 and you'll go down the backbone to whatever number carbon you get to. And then in your Haworth projection, this carbon on the right here will be your number 1 carbon and it'll go around and number that way. And then converting from the Haworth projection to your chair conformation will be pretty similar. And all you have to really do for that one is just make sure that you follow the axial equatorial pattern. So let's quickly go through an example of how to convert between projections. Okay. So if we start with the same molecule that we had on the old slide, sorry, just give me a second to write it up. So we have this Fisher projection. And so if we go ahead and number of carbons in the same way, we see that we have a 6 carbon backbone. And then converting between our Fisher to our Hayworth projection requires the cyclization of the molecule. And so in order for that reaction to occur, I'm going to go ahead and draw out the mechanism really fast. So you're going to start by protonating. Right there. Once you protonate, you're going to use your last alcohol to come around and attack that first carbon. And then this will give you this like kind of fake form, but I'll draw it out like this just so that you guys can see. Sorry, that's an O. And then it'll cyclize around like that. And the reason why I have this squiggly right here is because the stereochemistry right there is undefined, because once you attack that carbon, it could go in either direction. Okay. And then once you have it here, you can go ahead and draw it in your Hayworth projection just by rotating your bonds a little bit. And so if we number our carbons again, just so that we don't lose anything. Right here. Then you can go ahead and figure out the pattern for how your, what direction your alcohols will be. So Juan, do you want to share that like thing that you say?
Well, a lot of you guys know by now, but remember, whenever you're having a bad day, you just have to downright uplift your friends. Or like when your friends are having a bad day, just downright uplift them. So downright uplift, lift sounds like left. So if it's pointing down, you go to the right. If it's pointing up, you go to the left.
Cool. So if we look at carbon number 2, it is on the right-hand side. So it's going to be going down. Carbon 3 is on the left, so it'll go up, and then you'll follow the same pattern. For carbon 5, remember that you can rotate. So if this oxygen is being rotated into the circle, you can rotate freely like that. And so your 6th carbon will actually be on the left, which means that it'll go upwards. Okay. So then once you have this Hayworth projection, you can pretty quickly turn it into your chair conformation. So your anomeric carbon, let's just say that it's going upwards. And then if that one's going upwards, then the next one's going down. Yes. And then the 3rd carbon is going up. Carbon 4 is going down. And then carbon 5 is going up. Okay. So this is our anomeric carbon. That's the one that the stereochemistry will change. And so in this conformation, since it's going upwards, it's your beta anomer. And then you can also draw the other version where it goes downwards. And this is your alpha anomer. Okay. All right, so that was just a quick review onto how to convert between your Fisher, Hayworth, and chair conformations. Are there any questions right here?
In the alpha chair conformation, is that OH on carbon number 1, is that axial or equatorial?
For your alpha, this one is axial. I just remember it because they're both A's. And then your beta is equatorial. Cool. Were there any other questions?
For the CH2OH, like, isn't always going to be up like that?
Yeah.
Oh, okay. Thanks, Juan.
Okay. Cool. I'm gonna keep moving. So this slide has kind of a review of just like in words of what I just did, but it is just showing the cyclization process. So your first step is to protonate your carbonyl like usual. Your second step would be your alcohol coming around to attack. And then we have this weird cyclized form, and then we can just use the downright up left rule to transfer it into your Hayworth projection. All right. So then we went through this already. You will form anomers, which are just your two the two versions of that primary carbon of the number one carbon. Yes. So your alpha anomer is when it's going downwards, and this one will generally be your axial version, and then beta will be upwards, which generally is your equatorial position. Okay. Any questions on all of those projections? Because
You
next we're
said that
going,
beta is down, right?
sorry, what?
You said beta is down, right?
Beta is upwards, and that's usually the equatorial position. Oh yeah, what Juan was just waving, one of the professors does it. I like the alphabet a lot, which is why I just think alpha is axial. But apparently one of the professors writes his alpha as like going down first, and so that's why it's like down. And then the beta, he like starts from the bottom and goes up, and so that's why that is upwards. Whatever floats your boat. Yeah. All right, I'm gonna keep going. So next we're gonna go into a bunch of reactions, and it's fun. All right, so the first reaction that you need to know is epirimization at carbon 2. And so all this reaction does is to invert the stereochem at your C2 position. And so remember that if you go ahead and number these, your C2 position is this blue carbon, or the blue line, and you're just flipping the stereochem right there. Okay, so then quickly the mechanism for this. All right, I just drew the top two carbons because I don't really want to draw out the entire sugar. But you're going to be under mildly basic conditions, so like NaOH, that will come in to deprotonate your hydrogen, and those electrons get pushed up to your oxygen. Just like that. Okay. Once you're here, these electrons will come back down. The electrons in that double bond will come out to grab another hydrogen. And in this attack, you'll go ahead and flip your stereochem. Okay. And then just one thing to note is that you're actually going to get a 50-50 ratio for each version in your product. Okay. Cool. The next reaction that you guys will have to cover is the conversion of glucose to fructose. And the key intermediate that you pass through is your enediol. And it's under mildly basic conditions again. So if we go ahead and look at this reaction, I am again going to just abbreviate the sugar. But we're starting with glucose. You're going to go ahead and deprotonate again. Okay. Once you're here, these electrons are going to reach out to grab a hydrogen. Okay. And then from here, another equivalent of base will come in to grab your hydrogen and then send these electrons out to grab a different hydrogen. All right. And then this allows you to create your fructose. Like that. Okay. And then the intermediate that you wanted to take note of is that right here, you have your ene diol. And the reason why it's called that is because you have two alcohols, which is the diol portion, and then the ene is when you have the double bond in between them. So that is the conversion between glucose to fructose. Next, we have glycoside formation. And so this occurs when you convert that anomeric alcohol. So at your 1 position, your alcohol gets turned into an alkoxy group, so any OR group. Right. So the reaction for this one, I'm again going to abbreviate the sugar, but your first step will be to protonate. So you're going to protonate to water, which makes it a good leaving group. The electrons on your your internal oxygen will come down to kick off your good leaving group. And so we get a double bond formed in here. Once we have this intermediate, whatever OR group we want will come into attack to relieve the positive charge. And when we attack, we're drawing a squiggly because it could go to either side. And then last, you're just going to deprotonate. Okay. So again, here you can have either your alpha anomer or your beta form. And this is your glycoside.
Could you please go over why one of them is more stable? Because I know like one of the like axial or equatorial, like one of them is more stable, but I don't really understand why.
Okay, yep. So when you have your two anomers, like this is your alpha form and this is your beta form. So under normal circumstances, you would expect it to be heavily favored towards your beta form because your equatorial position has the least steric hindrance. So if you think back to like Orgo 1 material when we were talking about energy levels of chair conformations, your equatorial position will have the least interactions generally. And so that's why it's more stable. Called the anomeric effect shows that there's additional stabilization for the alpha anomer that is a little bit unexpected. And so instead of seeing a heavily favored beta anomer, you're going to see more of a 50-50 almost, but a little bit more heavily favored towards the alpha form than you would anticipate. And the reason for that has to do with pi orbitals, which I'm not sure to what extent you guys need to know. But pretty much like at this carbon and then this oxygen, there's going to be a favorable overlap of your pi orbitals right here, just due to the angle of the bonds. And so when you have this overlap right here, the electron density from that lone pair on your oxygen is going to be able to overlap with this one. So think hyperconjugation when we were talking about C+, what is that? Carbocations. Yes, think hyperconjugation. And so since you have that additional stabilization by sharing of the electron density, then your alpha form becomes more stable than you would anticipate. Okay. All right. Then moving on to the next part. The next reaction that you need to know is reduction to alditols. Alditols? Yes. And so alditols are when you have two terminal alcohols. So if we look at our final product, we've changed both the first carbon to your alcohol, and then you've maintained the alcohol down here. Okay. So then let's go through the mechanism for this one again. Key thing to remember is that we want two terminal alcohols. And since we already formed the bottom alcohol, because that's in our starting material, I'm just going to focus on the top one. And so we're really just doing a reaction to reduce that aldehyde to an alcohol. So we'll be using NaBH4. This hydrogen will come into attack and then send those electrons up. And then you'll come in with your workup, just to protonate. Sorry. And then form that primary alcohol up there. Okay. So that is with NaBH4, which makes sense because you're just reducing your aldehyde to an alcohol. All right. And then the next reaction that we're going to go over is oxidation to aldonic acids. So your aldonic acid will contain one carboxylic acid. All right. So if we go ahead and look at our product and compare it to our starting material, we've formed a new carboxylic acid up here, but we have maintained our alcohol on our 6 carbon terminal carbon. So the reaction for this one to form one carboxylic acid, we're again going to focus on this top aldehyde. And so we're just doing an oxidation of that aldehyde. So first step, like usual, when we're under acidic conditions, we're going to protonate. Once we're here, another equivalent of water will come into attack and relieve that positive charge. Okay. From this step, we're just going to have a proton transfer to deprotonate. So another equivalent of water will just deprotonate that. From this step, we now have our Br2. So a lone pair on oxygen will come out to grab a Br and then kick off that leaving group. And then you're going to have another proton transfer to deprotonate. And then last, you'll have one more equivalent of water come in to deprotonate that hydrogen, swing these electrons around to form a carbonyl, and then kick off your good leaving group as Br-. So that will go ahead and form your carboxylic acid. So using Br2 and H2O, you can go ahead and oxidize your aldehyde into a carboxylic acid. Okay. Yell at me if you need more time, otherwise I'm going to keep going.
Could you just leave it here for next?
Yes.
Sorry, where does the negative H plus come from again?
Oh, that's just a proton transfer. I'm saying minus H plus. I can write it out as well. Sorry, I was getting lazy. All that's happening in this step is that another equivalent of water comes in to deprotonate. And so, yeah, that hydrogen is just plucked off. And that's the same thing that happens down here. Okay, I'll give it just a couple more seconds and then we'll keep going. Okay, so the next reaction that you guys covered is oxidation to aldaric acids. And so these are when you have two carboxylic acids. So comparing your starting material to your final product, you can see that we oxidize that aldehyde into a carboxylic acid, and then we also oxidize down here. Okay. And all you really need to know is that this happens with HNO3 and heat, but I don't believe he covered the reaction mechanism in lectures, so we're not going to go over it. Key point is just HNO3 with heat turns into two carboxylic acids. Okay. The next one is your Kilani-Fischer chain lengthening synthesis. So all that happens here is that using KCN with HCN and then applying H2PDC. Sorry, not PDC. H2PD BaSO4. Yes, different. And then an acid workup, we'll go ahead and add one carbon to your chain. Okay. So the reaction mechanism for this one, I'll go ahead and draw it out. You're going to start by protonating your carbonyl. Next, your CN minus will come into attack and relieve the positive charge. From here, you're going to apply H2 PDB, that was a B, ASO4. And that will reduce your nitrile. Okay. And then from this step, now you're trying to get rid of that nitrogen. So we're going to do a series of protonations and attacks to get rid of it. So we'll start by protonating. Water will come into attack. Oh, I realized what I messed up. There should be an H already here. And so once you protonate again, it'll get to 2. What? Yes. Okay, cool. So there's 2 right there, and then you just attacked with your water. Okay. And then from this step, you're going to do a proton transfer. So the H will get kicked off the water, and then you're going to have another H added to your NH3. And then this will be protonated, which makes it a good leaving group. So once you form your good leaving group, this will come down and kick off your leaving group. And then your last step right here is just to deprotonate again. Cool.
Should that bottom OH become like the squiggly thing after adding the HCN? Since we have 2 products.
Yeah. So the center right here, which becomes right here, is the one that could flip your stereochem.
Also, not to be nitpicky, but your third molecule, the CN bond, is not linear.
Oh my God. I cry. I should be fired. Don't fire me. Nobody tell Falzone. We're better now.
Do we not need to know like the H2 PDBA SO4? Do we just need to know that that's like reduction? We don't need to know like exactly what happens.
Yeah, so that is a radical reaction, so you do not need to know it. All you need to know is that it reduces your nitrile down.
I'm sorry, what was the mistake that you just corrected? I think I missed it.
Oh, make sure that your triple bonds are linear because they're sp hybridized. So they should all be in a straight line. I cry. Yes. All right, any other questions on this one? Okay, I'm gonna leave it up for just a little bit longer in case you're still writing, and then we'll keep going.
Is there a product that is favored more?
In this case, I think it should be 50-50, but someone can correct me. I'm like pretty sure it's 50-50. Okay, we're gonna go with it's 50-50, but you should probably not quote me either. All right, I'm gonna move on in like 3 seconds. Okay. So then the next reaction that you guys covered was the wool degradation. So this is chain shortening. And through this reaction, you're going to lose one of your carbons on the backbone. So the agents that you'll want to use is NH2OH with trace acid, and then AC2O, which is, with its component NaOAC and heat, and then base at the end. Okay. So the mechanism for this one, I'll go ahead and draw it out again. All right. In your first step, you're going to use NH2OH, and that will replace your carbonyl. So that was just like your imine formation, just like one of those reactions. Think back to exam 2, I believe, and just pretend that this OH was your R group. Next, you'll add in ACOH, NaOH, and heat. And this is just your substitution reaction. And all that, it'll be a substitution reaction for your alcohol. But then up top, it'll go ahead and reduce to your nitrile. And then next you'll add in that base to create a gem diol. And then your gem diols will always collapse down into your aldehydes. Okay. So you see that you lose one carbon on your backbone there.
Did we learn about that second reaction? I don't know if you mentioned it before.
Okay, the second reaction, when you have your NOH and then your H right here, this guy just looks like this. And then this guy, oops, did I write this wrong? Yeah, I did write it wrong. OC. This guy looks like this. Okay. So the first thing that'll happen is just a quick substitution reaction. And so instead of having your alcohol, you'll bond it like this. Okay. And then from here, Juan, correct me, is it another equivalent that attacks to kick it off?
Yes.
Another equivalent will come in, grab that, and then these electrons will get kicked off. Or sorry, this leaving group gets kicked off. Is that correct?
Yeah, that's good.
Okay, chill. And then that's what forms your, sorry, my arrows are unclear. This guy is the one that grabs the hydrogen. These electrons in the hydrogen form your third bond, and then your leaving group gets kicked off because this guy right here is very stable. Okay, And so then that's how you form your nitrile right there. Did that make more sense? Sorry, it's a little messy.
That makes more sense. Thank you.
Okay, yeah, I'm just gonna draw a little barrier. All right, I'll give you guys a little bit longer to draw that one down, and then we'll keep going. Okay,
I have a question.
yep.
So in the mechanism you drew, how did you go from getting the OH to an OAC?
Okay, that is just your substitution reaction. So you'll go ahead and is it protonate? No, you'll go ahead and attack with it, and then you'll do a proton transfer using this proton right here, and then you'll kick off your leaving group to get that one
Thank
switched.
you.
Okay. Then there's only a couple more reactions for this segment. Next, you'll have your polyether formation. So all you really need to know is that you have an R group connected to iodine, and then you're using H2O. And then all of those will go ahead and convert all of your alcohols into your ethers. So going from an OH group to an OMe. And it affects every single one of them on your molecule. And then a very similar reaction is your polyester formation. And so that was what we were just showing. And in this case, you're going to convert all of your alcohols into this ester group where it'll look like that.
Do you mind going back to the last slide for just a quick second? Okay, thank you.
And this one will affect all of them. And then there's a couple different ways to do it. You can also do it with acyl chloride and pyridine, but that will give you the same result. Cool. All right, this slide is just a summary slide. It's not terrifying, but we just went through all of the reactions and mechanisms, and this is just a summary of the product will look like and then what catalysts you should probably use. So then, are there any questions on any of those that you wanted me to go back to or answer? Okay, let's keep going. We're getting through it, guys. It's okay. So next we're going through catalysis. So the big one that you need to know is serine protease. And then we'll go through a couple examples of different types. Let's start with that. So serine protease is just one of the catalysts that Falzone really loves. And so it's shown up on a bunch of exams. But all you really have to know is that there's a bunch of proton transfers. So The electrons on this oxygen right here are going to form a bond with that hydrogen. These electrons will come down, and then this double bond will go ahead and attack your hydrogen of that serine in the enzyme. And then these electrons will come over to attack that amino acid of interest. And then these electrons will go upwards, and then it forms these hydrogen bonds in the oxyanion hole, and these hydrogen bonds will stabilize the molecule, the intermediate. Also, this problem will be on the problem set this upcoming week. So if you have questions, hit up your pile leader. Okay, so that was the first step. You're gonna do this process twice pretty much, but after your first step, you form this intermediate I had shown. And then once you have this, your electrons will come back down, and then you're going to break off your N-terminus by attacking that other portion of your enzyme. And so you're going to cleave the bond right here. Okay, so that was your first process. You're going to get rid of your N-terminus. Okay. And then the next step for this reaction is that you're going to do the tetrahedral intermediate once more. So these electrons are going to come back out to grab a water, and then this water will go ahead and attack your carbonyl, sending those electrons up to form this negative charge, and then you're going to be stabilized by hydrogen bonds again. Okay. And then your last step of this mechanism is to send these electrons back down so that you can cut off your C-terminus. So then that is how you get your pieces from that serine protease enzyme. Very cool. All right, and then we have some examples. So glucose 6-phosphatase isomerase is a type of serine protease. And so when it enters your enzyme active site, it'll go through this process and then break down into fructose 6-phosphatase. Phosphate. Okay. Another example that we'll see is aldolase. So that'll cleave between your C3 and C4 carbons. And the reason why it's called an aldolase is because it forms an aldol as the product. Yeah, cool examples. This segment you should probably just memorize, but you have 3 types of enzymes: trypsin, chymotrypsin, and elastase. And these will cleave different side chains. So it'll cleave on the C-terminus of these different amino acids. So trypsin will cleave basic side chains. And so these are your lysine and arginine. Remember, you don't have to memorize the structures of these. So, but you should memorize that they are basic or aromatic or nonpolar and small. And then chymotrypsin will cleave aromatic side chains. So these are phenylalanine. Also, guys, I don't remember my amino acids. So yes, these 3. And then elastase will cleave these 4. And you'll see elastase on your problem set this week. Hint, hint, wink, wink. Chill. I know. All right, next up. Can we keep going, please? All right, lastly, we have glycolysis. So I believe he's going to be covering this in class on Monday, I think, if he hasn't already. And I just have a bunch of slides with each of the steps. And I think your most effective use of time would just be to review these and maybe memorize them. But yes, so in glycolysis, you have, I think, 10 steps. And your first step is that your glucose is phosphorylated using hexokinase. hopefully he covers trypsin and all of that on Monday, but you'll also see it on the back test for sure. Yeah, okay, glycolysis first step. And all that happens right here is that your carbon 6, which is this guy right here, is going to get a phosphate handle, which is this guy. Okay. Step 2 is when it gets isomerized to fructose 6-phosphate. And so, yes, it goes from glucose to fructose. Okay. Your third step is going to be phosphorylating the other primary alcohol. So this guy right here, which you just formed because you converted into fructose, is going to get phosphorylated. Step 4 is using aldolase, which is one of the serine proteases that we just talked about. And it will cleave fructose into G3P and DHAP. And then your step 5, which converted right here, is the conversion between the two. Okay. Step 6 is just the phosphorylation of G3P. Yeah. So this guy right here will get phosphorylated again. Step 7 is using ADP, and it forms an acetate. Very cool. So your phosphate group becomes an acetate. Step 8 is when you transfer it to C2. So from right here, it's going to move up to your C2 carbon. Okay. Step 9, you're going to produce this using enolase, which does a beta elimination. So your elimination occurs here, right, using the alcohol. And then your last step, oh shoot, I skipped it. Your last step uses a tautomerization and gets rid of your phosphate. Okay, cool. That was like a speed run through glycolysis. It was very interesting for all of us. All right. Are there any questions on glycolysis? Okay, incredible. So that was the end of the show. And now we have a couple minutes to, or sorry, like 40 minutes or however long you guys want to go over any of your questions for any of the material that was covered during the course. So all of us are available to answer. You can feel free to put this in the chat or just speak up